So here is a sequent, a representation in sentential logic, this language of sentential logic of an argument. It's an argument that has three premises, and there after the turnstile is the conclusion. What kinds of sentences are these? This is a conditional with an atomic sentence as its consequent and a disjunction as its antecedent. This is another conditional with an atomic sentence, the same one as the consequent of that, and a negation as its, so the atomic sentence is the antecedent, and negation of an atomic sentence as the consequent. And this is a conjunction of two atomic sentences, and so is the conclusion. And now, how many atomic sentences do we have? 5. So the whole table will have 32 lines, because 2 to the 5, 2 to the power 5 is 32. So we could do the whole table, and then after we've finished it, so to speak, go through each line and say, is this a line on which the premises are true and the conclusion is false? Is the next line, and so on, until we find one, and then we can say the argument, the sequent, is invalid. But because we're just interested in one particular line, kind of line here, we can take a shortcut. We could say, is there a way of assigning truth values here, t's and f's? Is there a way of putting some combination of t's and f's here that will give us true here for the first premise, true here for the second premise, true here for the third premise, and yet give us false for the conclusion? If we can find a way of assigning t's and f's to p, q, r, s, and t that makes the premises true, but makes the conclusion false, we'll have shown that it's possible for the premises to be true while the conclusion is false, and so we'll have shown that the sequence is invalid. This is what we call an invalidating assignment of truth values to a sequent, is one that produces all true premises and a false conclusion. Well, if we look at the first premise and the second premise, those are both conditionals. And there are 3 ways for a conditional to be true: true antecedent, true consequent; false antecedent, true consequent; false antecedent, false consequent. The only assignment of truth values on which a conditional is false is when the antecedent's true and the consequent is false. So there are 3 ways to make the first premise true. We could put true for this disjunction and true here, or we could put false for this disjunction and true here, or we could put false for this disjunction and false there. The same is true for the second premise, because it's a conditional, right? Of course, if we made R true in the first premise, then we'd have to carry that same truth value over to the second premise. Same thing's true for S and not S and S over there. So when we're following this method with truth tables, we want to do the least work possible. And so we start where we have the least choice possible. And if you look at the third premise and also at the conclusion, those are both conjunctions. There's only one way to make a conjunction true, namely to make its left conjunct true and its right conjunct true. So we can immediately, so to speak, put t's here, because if we had an f here or an f here, then the third premise would be false. And we're trying to find an assignment on which all the premises are true. So we're only interested in the lines where S is true and T is true. And now with the conclusion, there are 3 ways to make a conjunction false, right? We're trying to make the conjunction, the conclusion false. But given that we're only interested in lines where t is true, there's actually only one way to make the conclusion false now. If t is true, then the conjunction both p and t could be false only if p was false, right? So we can also put in f here. Now, if we take the truth value that we assign to s here, true, and we look at the second premise, we see that not s is the consequent of the conditional. So if s is true, not s is false, right? So the second premise is a conditional, and we have to assign false to its consequent. Now, if its antecedent were true, the conditional would be false. We wouldn't get t here. So its antecedent must be false. And so we can fill in the truth value for r, f. Now we do the same thing. We take that f for r and put it here. And the same pattern occurs. We have a true conditional with a false consequent must have a false antecedent. False. And the antecedent is this disjunction, either P or Q, and there's only one way to make a disjunction false. 3 ways to make it true, 1 way to make it false. The only way to make it false is to assign false to P and false to Q. And so finally, we can put in this F here, and we have now found an assignment of truth values to P, Q, R, S, and T, namely false, 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 true, true, on which the first premise is true, and the second premise is true, and the third premise is true, and yet the conclusion is false, and so this is an invalid argument, or an invalid sequent representing an invalid argument. And this assignment of truth values is an invalidating assignment. An invalidating assignment of truth values to the atomic sentences that produces all true premises and a false conclusion. And so instead of having to do all 32 lines, go through them, we, so to speak, flip the method on its head. We say, can we find an assignment that gives us all true premises and a false conclusion? And here we could. And so the rest of the table is completely irrelevant. Are there more lines on which the premises are true and the conclusion false? No, I think we had no choice at any point. So this is, of all the 32 lines in the table, this is the only one that produces all true premises and a false conclusion. It would be pretty far down in the table, and so we've saved ourselves a lot of work by flipping the method on its head, if you like, searching directly for an invalidating assignment of truth values. And if we find it, it's an invalid argument, and we've done our job as a logician. Right? If we can't find an invalidating assignment, that's presumably because the argument is valid. Our failure to find it is an indication that it's valid. Of course, we'd have really to do the whole table to demonstrate that there wasn't an invalidating line. And this is why, rather than using this method to demonstrate validity, we instead use the proof method to demonstrate that arguments are valid. But this method is, in a way, a quick way of searching directly for an invalidating assignment and then determining, if we find one, that the sequent is invalid, represents an invalid argument. So that's what is called the indirect truth table method. So say, in a way, it's not a very good name, because what we do is, instead of doing the whole table, we can search directly for an invalidating assignment.